So, in the last discussion, we discussed how any function can be expressed as a linear combination of Mercer kernel function, that is any function in a reproducing Hilbert space can be represented using a linear combination of Mercer kernel functions. Now, does this result, which is the result of the representer theorem, is this result useful within the regularization framework of the regression problem? That is, I have a standard error in my regression problem that I want to optimize, subject to some regulatory conditions that obey certain monotonicity properties. Would this representation using the representer theorem be a solution to this optimization problem? That is, I want to minimize my standard error over the regression problem subject to certain regulatory conditions. Let us see this as a practical application of the problem that we deal with data. Okay. So, I state the theorem as follows, and we will see the proof details. So, f of x j, as we discussed earlier, is basically a linear combination, that is, this function in this reproducing kernel Hilbert space is a linear combination of Mercer kernel functions. So, f of x j is summation I equals 1 to L a I, the kernel function acting on data points x I and x j. This is my starting step. So, this representation from my representer theorem is the minimizer of the regularized empirical risk given by E of f, which is 1 upon 2 n summation I equals 1 to n. So, what I do is I take the square error, and the error is basically the deviation of my desired response with some unknown function that needs to be estimated, right. So, the desired response is a function of the data, and I formulate my my error criterion this way. This is my standard error, and f is unknown, and xn and dn are my data pairs. I also have a regularity condition which is given by omega, the norm of this function in this Hilbert space, and this could be an integral norm, etc. So, a subtle detail here, these data points n goes from 1, small n goes from 1 to capital N, and these are my training samples, and this is my regularizing function. So, there is another property that the regularizing function must satisfy, and it must be a strictly, and I will mention this here, omega must be a non-decreasing function. So, we begin with a proof of this result. So, let us start with the following steps. The step 1 in the proof is as follows. Let f perpendicular denote the orthogonal complement to the span of the kernel functions. So, I take these kernel functions I equals 1 to L, and f perpendicular is the orthogonal complement to the span of the kernel functions. That is, I take the inner product of f perpendicular with k, and that is going to be 0. Now, every function can be expressed as a kernel expansion on the training data, right, as a kernel expansion on the training data, that is I compute the kernel functions at those data points along with this component which is f perpendicular. Like the way we did in the representer theorem, every function can be decomposed into one that is expressible, that can be expressed as lying in the span of the kernel functions, and then another component which is perpendicular to the kernel function. So, omega norm on this function in this Hilbert space. So, basically what I do is I construct omega as the regularizing function, and this regularizing function is operating over the norm of the function that I have in this reproducing kernel Hilbert space. And why I want to bring in this norm? Because I want to bring in some regulatory conditions on this function, right. Basically this can be thought about using this norm in the Hilbert space, and I can express f by f perpendicular and this expansion, kernel expansion. So, what I do is I expand this function out here. So, omega acting on the norm of this function, which is decomposed like this, summation I equals 1 to L a I kernel x I on a data vector which is indicated by dot plus a perpendicular component. Now, let us introduce another function omega tilde, which is omega tilde acting on the norm square over this space. This is equal to omega of norm of f on the space. I am just making this definition. So, therefore, omega tilde of norm of f square on this Hilbert space is omega tilde of, basically I expand this norm from my previous step here that I have, right, and this is given by this quantity I equals 1 to L A I kernel acting on x I dot plus f perpendicular this whole norm square this in this space. So, what I do is, in the next step I want to invoke Pythagoras theorem property, because now I take the norm of the sum of two functions and I can say that the norm of the sum of two functions, I can express this as the norm square on the two functions, and if I assume if bringing in the orthogonality criterion, I can, for optimality, I can simplify this further, right. So, in step 2, so I will write it in a new slide. We apply Pythagoras theorem. So, what we get is omega tilde of norm f square in this Hilbert space is omega tilde of norm summation I equals 1 to L A I kernel x I dot square plus norm f perpendicular square, right. This is a strict equality here, because I can break this function into two components and the projection of f perpendicular on k is 0, therefore, this is valid. Now, this is greater than or equal to omega tilde of norm I equals 1 to L A I kernel x I dot square if we set f perpendicular to 0, right. For optimality, if we want to set f perpendicular to 0, then what we have is omega tilde of norm f square on this Hilbert space is equal to omega tilde of this summation here. Right, what I did was set f perpendicular to 0 for optimality. Okay, now let us see how the monotonicity property can help us. So, step 3, in light of monotonicity, omega of norm of f is basically equal to omega of this norm summation I equals 1 to L A I kernel acting on this data point x I and this vector indicated by dot. Right, because what I did is I formulated the omega tilde of norm of f square is omega of f. Right, now I have everything in terms of omega tilde f square until the last result where I invoke the Pythagoras theorem. So, in lieu of monotonicity condition I just feed that back. So, omega on the norm of on the Hilbert space is basically omega of this norm, right. So, what it implies is for fixed A I belonging to R, the representer theorem is also a minimizer of the regularizing function given by omega norm f in this Hilbert space, provided we satisfy the monotonicity condition. So, this is a very important result, and this is where the connection comes from our representer theorem to what we would like to minimize as the standard error plus the regularizing term there, right. So, to summarize, so I would like to just briefly walk through the steps of the theorem that we did just as a recap. So, we start with the representer theorem, which says that we can express any function in a reproducing kernel Hilbert space as a linear combination of the Mercer kernels, and this idea in the representer theorem is also a minimizer of the regularized empirical risk given by this quantity, right. And the other condition that we want is this regularizing function must have the monotonicity properties. Now, what we are given is the data points x and dn pairs n equals 1 to capital N. So, our proof involves 3 steps. The first step is like what we did in the representer theorem proof, that is break this function f into 2 components, one lying in the span of the kernel functions and the other being orthogonal to the kernel function. So, what I do is I take the regularizing function which is omega of norm acting on this Hilbert space, and I decompose that f, expand it out in terms of the span of the kernel functions and the orthogonal complement. Then I bring in another function omega tilde which is acting on the norm square. And I want to bring in this monotonicity property here. Omega tilde which is acting on f, norm of f square is basically defined as omega acting on norm of f. Now what I do is I take omega tilde acting on norm of f and decompose this function f on the right hand side using the perpendicular component and the parallel component. And the reason for this parallel and perpendicular component is to invoke the Pythagoras theorem property in the next step. It naturally falls in place because the projection of one on the other is 0. So therefore this norm of a plus b, two terms a plus b, can be broken as norm a norm of a plus b square can be broken as norm of a square plus norm of b square, and that is what we did, that is what we did here, right, because the inner product of a and b is 0. So where a and b are our functions here. Okay, so now we plug this into this and we have one term which is dependent on the span of the kernel functions, the other is basically the perpendicular component. For optimality we set f perpendicular to be 0. So we just have the omega tilde which acts on the norm of the linear combination of these kernel functions, and that is what we need here. And again in light of monotonicity that we started off with this assumption, we can say that omega of norm of f is basically omega of the norm of a function which is expressed as a linear combination of the kernel functions. So which essentially means that the representer theorem is also a minimizer of the regularizing function provided we satisfy the monotonicity property. Okay. So a small detail that was pinpointed by my student here. So in the statement of the of this theorem here, I mentioned that this representer theorem is a minimizer of the regularized empirical risk. But when we discuss the proof of this theorem, we concluded that for a fixed AI, that is some constants AI belonging to real numbers, the representer theorem is also a minimizer of the regularizing function. So that is what was proved. But how to choose AI, that is these constants AI that minimize the overall empirical risk. So for that you have to plug these AIs into this empirical risk. So AI appears both in terms 1 and 2 of this equation E of f. So when you plug in f of xj, the AIs will drop into f that appears in both the terms, that is in the standard error term and in the regularizing term, and then you have to optimize for these variables AI that minimizes this empirical risk, overall empirical risk, and that is a small little detail. So if you are trying to set this up in this optimization framework, so here I just proved that for a fixed AI that this representer theorem also minimizes the regularizing function. But going one step further, if you want to optimize over AI, then you have to plug AI into both the terms in the standard error and the regularizing term, and then solve for AIs from that. Okay. So that completes the details here. So this is a very useful result, and because we are connecting the standard error along with the regulatory conditions to what the solution that we get from the representer theorem, right, and this is a useful result, and I hope this theory can be applied to what you see in practice.